In this video, we're going to talk about a different data structure called a hash table. So a hash table, looking at the motivation for it, in some ways, it's trying to solve the same problem that our binary search trees were. And that's basically to make searches faster. Okay. So in many programs we run into, and this document is out there on Canvas, we need to store and retrieve data quickly. We don't have time to go through a lot of calculations to figure out where it's at. Things such as looking up a student record by ID number, checking to see if a word's in a dictionary, or counting how many times each word appears in a document. Okay. So if we stored these things in an array or a linked list, um, we could get to a big O of n, meaning if we have 100 items, we may have to go through all 100 to find out if that's what we're looking for. So we've talked about a binary search tree, which helps. That can get us down to log n, which is significantly less than n, okay? But it still is going to grow, not really fast, but it's going to grow as n gets bigger, okay? So the search was on, basically, for a method that we could have even faster search times, okay? So someone had the thought, well, what if we could find an item in constant time, which is pretty much at or close to only one on average. So that's the design goal behind hash tables. Okay. So the big idea here is that the hash table is going to use some mathematical function that will take the key, and this is called the hash function. It's going to take the key, which could be an ID number, it could be a word, it could be whatever, and it's going to turn it into an index. We can use that index to put it into an array or a vector. Okay. So we can think of this as a direct address system. The index is always equal to the hash function. You send it the key, you have the index, and that's it. So once you have the index, you can store the key value pair in that slot. If I give it a 25 and it returns an index of 7, then I know to go to index 7 is where I'm going to put 25. Okay. If I'm going to search for it, if it's there, it's going to be in that index 7. Okay. That's the point. So here's an example. Let's say we want to store these numbers. Okay. That are listed on the screen there. And we have an array size of 10. The function we typically use for numbers is the mod based on the size of the array. Okay. Because that will give us valid values from 0 up to 1 minus the array size. That's what mod will do, and that's exactly what the array addresses are. Okay. So in this case, we're going to take the hash. So we have 10 is our size. Our hash function is going to be just the mod 10. Okay. So when we want to store 1, 2, 3, 4, 5, that the mod 10 of that, so the hash function returns a 5, it's stored at index 5. Okay. 5, 4, 3, 2, 1 has a hash function value of 1, index 1. 6, 7, 8, 9, 0, 0, it's stored at 0. 1, 3, 5, 7, 9 is stored to 9, index 9. 2, 4, 6, 8, 0, 0. So now we have a problem, right? We can't just store 24680 at 0 because that's where 67890 is stored. Okay. And that's what's called a collision. Okay. And the first way we're going to do our hash tables with an array or a vector, you're going to have collisions. Okay. So, well, you're always going to have collisions, just whether they're how we deal with the problem. That's going to be the question. Okay. So if you have a good hash function, meaning one that is quick to calculate, gives a unique answer, and spreads out the data, unique, not unique for the key, not unique among all keys, um, then you've got a good function. But even then, you're going to have collisions. Okay. If you have more keys than you do slots for those keys, then you're definitely going to have collisions. That's something that comes up a lot in computer science, and it's a mathematical principle called the pigeonhole principle. And what that says basically, if you have 5 pigeonholes and you have more than 5 pigeons, then at least one pigeonhole is going to have more than one pigeon in it. And it seems pretty simple and logical, common sense even, but it had to be proven so we could use it in our proofs. Okay. So we want a good hash function then. Um, and how we deal with these, let me go back up a little bit here. We have two main ways we're going to deal with these collisions. And this will be over the next two lectures, okay, or the next two classes that we're doing on this. So the first one's called open addressing, where we're going to use linear probing as a way to just find the next open slot in our array, okay? The other way is called separate chaining. With separate chaining, in each position of our array, we're going to have either a linked list or a vector. So they can hold multiple items and it's going to be fine. Okay. So we'll cover those in class. Okay. So when we're choosing our hash function, you want it to be have these characteristics to be good. It should be fast to compute. It should spread the keys as uniformly as possible across the table. And it should minimize collisions. Okay. So for integers, we typically do a modulus-based function, something like this. So we're going to send the key, we're going to send the table size, and it's just going to return the key mod table size. Okay. For strings, we typically are going to combine the characters into a weighted sum. Okay, so we're going to go through and we're going to take the string key and the table size. We're going to start with a hash value of 0. We're going to go through all of the characters. Okay. And remember, if we have a character, if we multiply it by 31 and add the character to it, okay, so the hash value, the original hash value, or the 0, sorry, times 31 plus C mod table size, this is going to give us the ASCII values of the characters. Okay. And when you mod it by table size, that's going to be the hash value that we're going to use. Okay. As far as the complexity, the big O complexity here, the insert into a hash table is average of big O of 1 or constant time, which is good. Worst case scenario, if you're on a linear probing and you have to go all the way to the end to see that there's no room, could be big O of n. Okay. And search and delete have the same big O of 1 on average, big O of n in the worst case. Okay. So when do we use hash tables? If you need a fast lookup, for sure. When order doesn't matter, hash tables are not ordered in any kind of way. You're not going to have a sort fall out of a hash table in any kind of logical fashion. Okay. In networking, if we're doing routing tables, we often use a hash table. In AI and game programming, okay, if we're looking at calculating and caching or keeping track of the state of the board or some computed results, we can use a hash table for that. Okay. So one way that we can think of a hash table then is as a set of mailboxes, which are the array slots. Each one's labeled by a number. That's the index of the array. The hash function then is the mail sorter who can figure out where each one goes based on the hash function and going to put it into the right box. If two letters get in the same box, then we have a collision. We have to figure out a way to get around it, either through the linear probing or through the chaining. Okay. So let's talk about the first of those strategies, and that is handling collisions with linear probing. So when this happens, whenever a collision occurs, the algorithm is going to look for the next empty slot. Okay. We've got this formula here to help us figure that out. So let's look at this case. We're going to insert 27. It goes into index 7. We're going to go 18. It goes into index 8 because 18 mod 8 is 8. When we get to 28, it also wants to go into the index position at 8. Okay. So what do? We just push it to the next one. And this isn't the whole table. We would still have 0 through 9, and 0 through 6 would be still empty. But we now have the 8 has an 18, and the 9 has a 28. Okay. So if you were to search for the 18, it would calculate, you need to look in slot 8. There it is. If you search for the 28, it would say you need to look in slot 8. Say, okay, I'm not there. Let me try one up. Okay. Tries there, and there's your 28. Okay. When does it know to stop? It's going to keep looking, and it will go around back to 0 if it has to. Okay. Because if I then enter a 38, the 38 would go, the next available spot would be at 0. Okay. So it's going to keep searching until either it finds what it's looking for or it finds an empty spot. Okay. That's kind of how that works. So this works just fine, except when we go to delete something. Okay. So let's look at the example here with just this part of the table. If we were to delete 18, okay, we take 18 away. Okay. Now I go to look for 28. It says go to index 8. Well, there's nothing in index 8. Okay. So I would incorrectly assume that 28's not in the table when it's right there. Okay. You could try to move them all back around, but that would be really ugly, especially with a big table. Okay. So what we're going to do instead, okay, so this is just another example of that. Okay. We're going to use what are called tombstone values. Okay. And we get down to that somewhere here. Yeah, so here's the solution. Basically, a tombstone value will be some value that we know in our algorithm means that the slot, there's nothing in it now, but there has been before. Okay. So often our examples will use like a negative 99, assuming that could never be a value that's really there. Okay. So we now have three possible states for each of our cells. It could be empty, it's never been used. It could be occupied, there's a current value, or it could be deleted. There was a key, but now it's not. Okay. So as an example of this one here, so we have the same hash table we had before. Okay. In the example, I didn't go through, but in this case, we've got um, there's one at 10, there's one at 17, there's one at 24. Okay. And I think in this case, um, yeah, we had a three. All of these had a three. Okay. Because of the way it did the hash function, they all returned um, three as their value. Okay. So, which means that this goes here, the next one goes there, the next one goes there. Okay. If we delete the 10, okay, so that's where we're at down here. We've deleted the 10. So if I went to look for a 17, it would say look in three and it's not there. Same thing for 24. Okay. But in this case, they've got a little skull and crossbones here for the tombstone, but we'd have our negative 99. So if we delete it and replace it with a negative 99, if I went to look for a 17, it would say, okay, it's not here, but something was. Let me keep moving. Okay. So it's not empty. Same thing with the 24. Okay. Note that um, when you have a new key, then you can go ahead and reuse that tombstone. Okay. So if I deleted 10 and I added 10 back, I could put the 10 right where it was, or anything else that has the hash value of 7. Okay. So the negative 99s or whatever you're using can be reused. Okay. So with the linear probing, it can be relatively effective. It works okay, but it works best when you have a lot of room in your table. So you want your table bigger than you need it, okay, to have some room to move things around. So the second way we can do these is through the idea of open chaining, okay, where instead of just finding another slot, we're going to have in each cell of our array, so in each position, we're going to have either a linked list or a vector of elements. So we keep adding to it, okay? So in this case, in our above example, when we had the 27, we went to add again the 37. Oh no, sorry, this is a mod 10 example. There we go. So the 27 with the mod 10, you just go to the last digit is a 7. It goes here. 18 goes there. Okay. The 37 goes here. There's already one there. So you add it to the chain, either the linked list or the vector. Okay. 28 gets added to this one, and 47 will get added here. Okay. So now when you go to search for the 47, you would look here, it's in this spot. So I'm going to search this entire chain looking for it. Okay. So the worst case scenario here in the linear probing, the worst case scenario is in. You may have to go through the whole thing. Okay. And if you get full, you've got lots of trouble. Okay. But with the open chaining, the worst case scenario is the length of the longest chain. And that could be in. If you input 100 items that all go to the index of 7, you're going to have one big long linked list or one big long vector. Okay. But in general, it's going to be better performance. Okay. So to summarize all this stuff, and then in class we'll do more of the actual um, hands-on work of it. Okay. The collision handling, the options we have, linear probing, take the next free slot. Open chaining, it's a linked list and same index. Okay. With clustering, we have to worry with linear probing. The clustering could be the hash function could put a lot of values close together, and that makes the performance go down. We don't have a problem with the open chaining. Okay. With deletion, we have to have the tombstone marker or we're going to lose data. With open chaining, just remove it from the list. No big deal. We know how to do that. Okay. Space usage, the linear probing has a fixed array, whatever its size is. With open chaining, for the same amount of data, we have some extra memory for pointers, but it's not significant, but it allows us to grow and shrink as we need to. The performance will degrade at high loads on the linear probing, no doubt. Where open chaining will degrade, but in a more graceful manner, which it means it's more predictable. Okay. I do have a little example spreadsheet of how this can kind of work. Okay. So here's a linear probing example, and I've got a table size here of 10, and my hash function is the mod 10. Okay. So if I want to store 56, for example, okay, and my function is not working anymore. Oh, that was my function. Let me get it correct. Is that my function? Don't you love when your spreadsheet works and it doesn't work? That's my function. There we go. I'm over here. I'm in the wrong spot. So if I put a 65, okay, that's going to be an input key of 5. So I'm going to go to index 5 and put my 65. Okay. Now if I put a 71, okay, that goes at 1. 71 is there. Okay. Now I'm going to put a 95. Okay. That's 5 also. Well, I can't put it here, so I move to 6, put 95 there. Okay. And now I put 1,235 also goes to 5. So the 1, 2, 3, 5 is going to go there. Okay. Now, if I were to search for 65, I would run the 65 through the function again, okay, which tells me to look in position 5. I would go here and there it is. If I'm looking for a 95, I would have to keep looking there I would find it. If I'm looking for 75, I would go there, there. It's not there. Okay. Um, if I would then put in something like 88, which goes here, and a search for 75 would now have to start here, go there, go there, go there. It would only know now that it didn't find it. Okay. And then if I would delete this one and look for a 95, go here, it's not here, it's done. Put in my tombstone value of negative 99, and now that's going to be able to work. Okay. So that's the idea. If we're looking instead at the open chaining, it would have the same functions with the hash function. So in the same example, if I put a 65, okay, and I can't see my numbers, let me see. Delete some of this stuff so it appears easier to get to. Can I see it now? Yeah, kind of. Let me delete a few more. There we go. Okay, so if I do like a 65 again, it goes to this one and it's there. And then I add a 95, whatever I'd said before. Then I add a 1, 2, 3, 5. That's all okay. I add a 75. It's all okay. Okay. And you can add as many as you want. These are, whether it's a linked list or a vector, you can just keep adding to the size. Okay. So now if I were to search for a 65, I go to my position 5. There it is. If I'm looking for any of those others, I keep looking. If I were looking for just a 5, I would check there, nope, there, nope, nope, nope. Now I'm done. Okay. So that's in general how it's going to work from a visual point of view. Okay. So that's it. Okay. For how we're going to deal with the hash tables. Okay. So we'll do some more work in class to work on the programming parts. Okay.